Holiday and Resonant, Chapter 8, Potential Energy, Conservation of Energy, Problem 30. A 2.0 kilogram bread box on a frictionless incline of angle 40 degrees is connected by a cord that runs over a pulley to a light spring of spring constants K equal 120 newtons meters, as shown in figure 843. The box is released from rest when the spring is unstretched. Assume that the pulley is massless and frictionless. A. What is the speed of the box when it has moved 10 centimeters down the incline? How far does the incline from its point of release does the box slide before momentarily stopping? And what are C, the magnitude and direction up or down the incline of the box acceleration at the instant the box momentarily stops? So first it wants the speed after the box has moved 0.1 centimeters. So first, let's just think about the amount of energy we have for the box to move. And that we're going to need the height the box is at when it moves at 0.1 meters. So let's look at this. We'll draw us a little triangle. And this is Y. This is what we're going to be looking for. And we know it's going to move 0.1 meters. And we know that this is 40 degrees. So we can say the sine of 40 degrees is going to equal to Y over the 0.1 meters. So Y is going to equal to 0.1 meters times the sine of 40 degrees. So that's all that's the height involved with this lunchbox moving. So we'll start off the potential energy initial is equal plus the kinetic energy initial is equal to the potential energy final plus the kinetic energy final. Now the potential energy initial is just going to be mgy. The kinetic energy initial is 0. It was not moving. So we have a 0. The potential energy final is going to be equal to the energy in the spring, which is going to be 1/2 kx squared, plus the kinetic energy final is going to be 1/2 mv squared. And we need to solve for v, so we'll this will go to 1/2 mv squared is going to equal to mgy minus 1/2 kx squared. And so v squared is going to equal to 2 times mgy minus 1/2 kx squared divided by m, and this will go to v, velocity, which we're looking for. It's going to equal the square root of 2, the mass is 2, times 9.8 times y that we figured out here, which is going to be 0.1 times the sine of 40 minus 1/2, and k is 120, so that's 60 times 0.1 squared, 60 times 0.1 squared divided by 2. I'll do these calculations and be back with you. Comes out to V equals 0.81 meters per second. So that's the velocity for part A. Now B asks, how far down the incline from this point of release does the box slide before momentarily stopping? So let's do that. So we know that we have spring potentially is equal to 1/2 kx squared. And we can reason and that mg sine theta, that's the force, times x, it's got to move the same distance that the spring stretch, that these two must equal each other when the box comes to a stop. So we'll say this will go to 1/2 kx squared is equal to, now you realize this is work, mg sine theta times the distance it moved. This is work. That's in terms of joule. And this is in terms of joules. It's equal to mg sine theta times x. This x will cancel, and we'll just have this. So x, that's what we're looking for, is equal to mg sine theta times 2 divided by k, which is 120 Newton meters. And I'll be right back after we do this calculations. All right, when you do the math on this, you end up with 0.2099 meters, which x is just going to be 2.21 meters. The trick to this is understanding that as it slides, it has a force of mg sine theta. If you multiply that by the distance, x, you get work. And then you could set the work to the potential energy, or B. C, it has the magnitude and direction up or down the incline of the box acceleration at the instant the box momentarily stops. So this is the same. I'm just going to draw it like this. Here's the spring. And we have the pulley here. We won't worry about, and then we have the box. The box is pulling this way, and the spring is pulling this way. So that's essentially what we have. So whether it goes back up the incline or down the incline depends on which force is the strongest. So let's just look at the spring force. It is, spring force would be minus kx. And that's going to equal a minus 120. That's given to us, Newton meters times 0.21 meters, and that's going to equal a minus 25.2 newtons back toward the spring. Now let's look at this force here that's pulling opposite of the spring. We have mg sine theta, which is going to be 2 kilograms times 9.8 times the sine of 40 degrees, which is going to equal 12.59. We'll just make that a 6 newtons. So we can see that the block is going to move up the incline. That's what the force, once it momentarily stops, the force is going to be pulling it up the incline. Now finally it asks for the acceleration. And we know that just from F equals ma, that the acceleration is going to equal to the force over the mass. Well, what is the force? The force is the difference between these. We got the spring force, which is pulling one way, and the mass, the gravitational force, pulling the opposite way. So that's just the difference. So A for acceleration is going to equal to 25.2 minus 6. Minus 12.6. And that's going to give me 12.6 divided by the mass, which is 2 kilograms, and that's going to give me an acceleration of 6.3 meters per second square. So that was this part D.